So for the final question of this paper, we have been asked to use proof by exhaustion to show that the following statement is true. Well, we have to show that n plus 1 to the power of 3 is always greater than 3 to the n. Now, the subsets of n that we've been given is that n is a natural number and that n is less than equal to 4. Now, natural numbers are all positive integers, not including 0. So that leaves us with the values of n that we can use to be n is equal to 1, n is equal to 2, n is equal to 3, and n is equal to 4. Now, all we have to do as to use proof by exhaustion is basically substitute each of these values into this equation until we have exhausted all of our values. So essentially, let's go ahead and do that. So for n equals to 1, we have to prove that 1 plus 1 to the power of 3 is greater than 3 to the 1. Well, is that true? Well, 1 plus 1 to the 3 is 8. Is that greater than 3? Yes, it is. So that is correct. For n equals 2, we have to do the exact same thing. 2 plus 1 to the cubed. Is that greater than 3 squared? Well, 3 cubed is 27. Is that greater than 9? Yes, it is. Same thing for 3. We have 3 plus 1 cubed. Is that greater than 3 cubed? Yes, it would be, because 64 is greater than 27. And finally, for 4, we have 4 plus 1 cubed. Is that greater than 3 to the 4? Well, 125 is indeed greater than 81. So therefore, we have proved by proof of exhaustion that this statement is true. You can write a little tag here, hence proved, to help the examiner know that you have proved it through this method. So that concludes it for part I of question 15. So for the second part of this question, we have been given that m cubed plus 5 is odd, and we thus have to use proof by contradiction to show using algebra that m is in fact even. So a good starting point here is to first take the statement that m is odd. So we can write a little assume m is odd here, and we can also assume that m is equal to 2p plus 1. Now, if we were to go ahead and substitute m into this value here, so we know that m cubed plus 5 is equal to 2p plus 1 cubed plus 5. So you can expand this in the following way. Well, we can split 2p plus 1 into a singular and a quadratic, so we can get 2p plus 1 whole squared plus 5. We can further expand this by showing that 2p plus 1 times 4p squared plus 1 plus 4p plus 5. Again, further expanding this again. So we get 2p times 4p squared, so that's 8p cubed plus 2p plus 8p squared. And then 1 times 4p squared, which is 4p squared plus 1 plus 4p. And then again, plusing 5 at the end there, not forgetting about that. Just join all the like terms together. So we have 8p cubed plus 12p squared plus 6p plus 6. So from this, we can see that since all of these terms are even, this whole equation has to be even. And this thus proves by contradiction that m is also even. By contradiction. Okay, and that concludes it for question 15.